Hello everyone, my name is Zekeriya. We are Team Hybrids, and our graduation project is called Hybrid Energy Harvesting IoT Sensors for Sustainable Agriculture. Supervisor Mehmet Karakaya and team members Ahmet Ogun Saloğlu, Emirhan Kara, Mümin Emirhan Darkan, and me as a team leader. Our team formation process formed randomly but adapted quickly. After meeting with supervisor, we distributed responsibilities according to our multidisciplinary skills. Let's talk about needs identification. First, we need a more stable energy production system. We wanted smart optimization using real-time operation system and environmental sustainability. Also aimed for 24/7 continuous operation, independence from the electrical grid, and without human intervention. The main problem is that many smallholder farmers cannot access affordable precision agriculture technologies. Most traditional irrigation systems waste water and energy because they are manually controlled. Our project aims to solve this problem by developing a cost-effective and energy-reliable smart agriculture solution. Now I will talk about the system requirements. Functionally, all systems should measure environmental data such as soil moisture, temperature, and humidity, transmitted wireless like Wi-Fi or LoRa, and system must operate in off-grid environments. Solar energy is used as primary source and wind energy for secondary support source. We also included a batteries for stable energy storage. Proposed concept is by combining solar and wind energy, the system can continue operating even when weather conditions change. This design improves sustainability, reliability, and energy independence for smart agriculture application.
Hello, I am Emirhan Kara. I will present our project's implementation. Our system uses a module designed for high efficiency. It consists of three main parts: energy harvesting, power management, and the ESP32 controller. We built this system to work automatically in rural fields without any human control. Our main energy source is a 12-volt solar panel. We also add a small wind turbine for extra support. We use an MT3608 module to boost the wind turbine power to 5 volt. All this renewable energy is stored in a 2500 milliamps hour battery to keep the system running 24/7. The most important part is our power management system. We use a CN3791 module for solar panels and a BQ25185 chip for smooth power transfer. This means if solar or wind energy stops, the system switches to the battery instantly, so the ESP32 never restarts. We use the ESP32 as our main brain. It reads sensor data and manages the Wi-Fi. We use a BMA280 sensor for temperature and humidity and a capacitive sensor for soil moisture, which is very durable in outdoor conditions. To drive the water pump safely, we designed a simple driver circuit. Since the ESP32 output is 3.3 volt, we used an IRLS44N MOSFET to control the pump. This protects our controller from electrical noise and high current spikes. For energy saving, we use deep sleep mode. The system stays asleep most of the time to save power. When the soil gets dry, the system wakes up, checks the sensors, runs the pump, and sends the data to the cloud automatically. Finally, all data is sent to the cloud using the MQTT protocol. Users can check the temperature, humidity, and battery stats on our dashboard. Thank you for listening. Now my teammate will explain the testing phase.
My name is Ahmet Ogun, and I'll talk about testing and demonstration. We validated our brand Hybrid across 4 areas as seen on the page, such as energy harvesting, sensing accuracy, actuation, and communication. Starting with the energy, the solar panel that we used delivered around 12 volts under the full sun, and the CN MPPT module maintained charging efficiency even under the overcast conditions. Also, the wind turbine provided supplementary power during low light periods. For sensing temperature deviation and humidity, they both fell under the acceptable thresholds shown in the chart. The soil moisture sensor was tested at 3 different levels and correctly triggered the irrigation threshold. On the actuation, the MOSFET switched the water pump from the ESP32 GPIO with no voltage drop or thermal issue. As you can see in the test table, all 4 scenarios are passed. For communication, the ESP32 published sensor data via MQTT and it's done under the 2 seconds per cycle. Soil moisture, temperature, humidity, and battery state of charge were all visible live on the dashboard. Here is the full traceability summary. As you can see, all 6 core requirements are verified and the LoRa long-range deployment is marked as planned. And about our limitations, wind testing was done only with the fan, so if we use real wind it will improve the results. And the long-term endurance testing is pending due to the time limits. And both LoRa module and the BQ charging IC were delayed due to custom issues. The energy management function was covered by existing circuits. Despite these constraints, Hibrix meets all the core requirements and ready to field deployment.
Hello, I am Mümin Emirhan Darka. I will present cost analysis, commercialization, standardization, safety, multidisciplinary aspects, and SDGs. First, regarding the cost analysis of our project, the expected cost of the system was estimated as approximately $70 during the design phase. However, the actual prototype cost reached about $102 due to additional implementation requirements such as enclosure materials, wiring, batteries, and supporting hardware. Despite the increase, the system remains relatively affordable compared to commercial smart irrigation solutions. For commercialization, our design used widely available and low-cost components such as ESP32 microcontrollers, environmental sensors, renewable energy modules, and standard electronic components. This makes the system suitable for mass production and scalable for different farm sizes. The primary target users are small-scale farmers, greenhouse operators, and agriculture business looking for effective smart irrigation solutions. This project has also strong interdisciplinary dimensions. Electrical and electronic engineering was applied for circuit design, power management, and renewable energy integration. Agriculture contributed to irrigation requirements and environmental monitoring needs, while computer engineering and IoT technologies were used for cloud communication, data processing, mobile application development, and Gemini AI integration.